microplastic in wastewater system. And then I'm going to present you some a study that we did trying to improve the removal of microplastics from wastewater system. Oops, okay. Hold up. Okay, so let's start with the first. So most of you are familiar with this water cycle. I bet you have seen in several since fourth grade, maybe, that they talk to you about that the water, it's in the liquid form, that it gets evaporated, rain, and it looks very pretty, very romantic. But in reality, so we know that the water is really, this gives us already an idea that the water moves from different environmental compartments, and then we know that there is a finite amount of water, especially fresh water. There are not that much fresh water as a fresh water, in the world. But all of that is cycling in this in the natural system. Now, an urban system is going to look a little bit more messy. We have the water. We take water, either water supply. It could be either surface water or groundwater. That clean water is going to be transported to your house or the city. When we use it, obviously, you are going to be, washing dishes, taking shower, going to the bathroom. You are generating some wastewater, and that wastewater has to be treated. Also, because of your house and all the impervious materials that we have in urban environment, contaminants are going to be accumulated, and every time that it rains, it's going to be collected in the stormwater runoff, and most likely we're going to discharge it, with very small amount of treatment to rivers or streams or any type of bodies of water. The wastewater that we produce is going to be usually go to wastewater treatment plants, and again, it's going to be discharged into different freshwater bodies or the ocean too. So again, if we see this is what we call the urban water cycle. And something that I want to emphasize here is that there is only one type of water. We already claimed that the water cycle through all these different compartments that we have in urban system. And in some way, we are all downstream of a wastewater treatment plant or a stormwater runoff, throwing this, contaminants. Even though we have some treatment, our treatments are far from being progress, even though we have done a lot of progress. So there are going to still be contaminants that are going to be released to natural sources of water. So again, that's something that in environmental engineering we're trying to emphasize is that, again, there's only one water, the water cycle through different urban compartments. So we should be thinking that we are always downstream some type of discharge or treated water. So also we can see it, every time that you see a report that in the drinking water you start finding antibiotics or other pharmaceuticals, the way that we release all of that is through, when you go to the bathroom and you release all the part of the, that's how it goes. There is some connection between this, wastewater that we use and the drinking water that we use. And again, one water cycle through the urban system. So before we start talking about microplastic, I want to put some of the progress that we have done in context. And I'm going to show this picture. This is the picture of the Cuyahoga River in Ohio. This picture was taken, I think, in 1969. And you can see that this is the river. I don't know if you see, but the river is on fire. The Cuyahoga River, this was not the first time that in 1969 was not the first time that this river got on fire. Actually, it started getting on fire since the early 50s. And this incident, it wasn't an isolated incident in natural bodies of water in the US by that time in the early 70s. This was a common scenario that it was happening. Because of this, I mean, this got very famous because it happened to be reported in 1969, and they started doing a whole journalistic research about it. And actually it ended up to be a very important article in the New York Times that it then developed, it created all this environmental movement in the US that it leads to the Earth Day and also to the Clean Water Act in 1972. So let me show you that this is what the river looks today. So people actually can go and use it for recreational uses. So some of the policies that we have implemented since the early 30s, so 70s. So this is not that far along. I mean, maybe some of your parents were young. I mean, so it's not that far along that we start implementing these regulations, and they have had an impact in the water quality and the water resources of the U.S. It's a perfect nod. We have to do more, but I want to make a case that we need to put it in context. The situation was much work, and policies and public awareness, make a difference, and we can, we see this difference in this 70 years, 11 more changes. Okay, so now let's talk about microplastics. And maybe already you have seen some of these numbers, but just to emphasize, I think it's so fascinating that we don't realize we use plastic so much during our day-to-day life, but we don't see the implications, what happened with all this material. Something interesting, and this is not uncommon for developed countries, the US is about 5% of the population, so very small fraction of the population, but it generates about 30% of the world solid waste. This is not unique. It's very common that developed countries produce large amounts of solid waste. The US is a little bit bigger than other countries, but in general, developed countries produce much more solid waste than non-developed countries. So another statistic, just to impress you, is like that you throw away during your lifetime, you're going to throw away about 600 times your body weight. And we use about more than 2 million plastic bottles every hour, just from drinking water purposes. That's another, I can talk forever to you about why we shouldn't be using plastic bottles when for quality reasons, and potable water is pretty safe in the US in general, but that's a topic for another day. But just one importantly, only 15% of these bottles are recycled. And again, this is not only for the bottle. In general, plastic, and we're going to see in other numbers, it doesn't get really produced, recycled too much. And again, one of you have seen in the news about plastic straws, that about 500 million plastic straws are used every day also in the US. Now, something important is what happened to all this waste. Most of this waste is going to be imported. Most of the recycling of plastic, it doesn't happen in the US. It happened in mostly the major activity was China. Interestingly, about in 1920 and 2017, there was a ban. I mean, China stopped receiving any plastic, and that has generated a very interesting situation here in the US. And most of the plastic that sometimes we claim that it's going to be recycled, most likely it's going to end up in incinerators because they don't really have any place. There are very, very few countries that they are accepting plastic waste at this moment. So, and that's also a topic for another possible webinar. But let's see about what happened. Plastic production since the 1950s. The amount of production of plastic had been increasing exponentially, and one of the main generators is the Asia region with about 50% of the plastic production. Something that I already showed you, not too much. Most of the plastic is going to end up in a landfill. Some of them is going to be incinerated, and only a small fraction is going to be recycled. And then compared to worldwide, the US, I have this two graphs comparing the global situation and the US situation. In general, the US, most of the plastic that we generate is going to be in recycling, even though what it seems to be that we have a large, household collection or recycling system, but it still is a very small amount that is actually recycled. So most of the plastic that entered to the ocean, I mean, since we are in the sea aim concept and we are interested on that, is due to mismanaged or fugitive emissions of plastics in the environment. And as you can see, most of them, it's going to happen in countries with a lower, low economic development, mostly because it's very expensive to have solid waste management systems. So most of the community, nobody want to be living surrounded by trash. It's happened because of a need, that there are not solid waste management systems. So most of this is going to be released into the environment, and usually, unfortunately, rivers and the ocean tend to be a common disposal location for some of this waste. So, so again, but still, only 0.9% of the plastic in the North American region is misplaced or they have fugitive emission. But however, remember that we are one of the larger emitters of solid waste. So it has to be also putting, these numbers are going to be a little bit different. You know, if we put it as a share of plastic waste, it will change a little bit. But still, we have so there are two issues here. You know, we need to pay attention and help communities around the world to solve the problem with solid waste management. And on the other hand, we as a developed country will produce a lot of trash. We also need to try to reduce our share and tap into our pretty good solid waste management system for most of the plastic trash. Okay, so are microplastic a contaminant? Actually, no. I mean, from the EPA point of view, there are two types of contaminants. I mean, the quality of water is regulated by two types of standards, the primary standards and the secondary standard. The primary standards are going to be contaminants that they had found direct link, proof link to human health. The secondary standard are usually going to be contaminants that produce some type of problem in the distribution system. You know, there might be salts that get accumulated or they precipitate, you know, hardness, color, maybe smell. Sometimes all of that, you know, contaminants that produce that characteristic not necessarily produce a human or a health risk. However, they might create problems in production, you know, when you use water for any type of production system, or, you know, when you are trying to, you know, to transport again the water in this pipe. So microplastics are not in any of these two regulations, actually, in terms of for drinking water. You know, even for drinking water, we don't regulate really. Microplastics don't fall in any of the categories. However, there is a category called the unregulated contaminant monitor rules that are suspect contaminants that they might have. We are not sure that they produce some type of health risk. And there are discussions in EPA to put microplastic into this category of the unregulated contaminant monitor. That means that they are going to be start collecting data about, you know, the amount and what type of microplastics are going to be present in mostly water for consumption. In the Clean Water Act, when we're talking this is more the first three standards that I was talking that are more for drinking water or drinking water sources. For the rest of the water, you know, any type of water resource is regulated by the Clean Water Act. And also the Clean Water Act doesn't have any specific regulation for microplastic. However, it has there are regulations regarding the disposal of trash in water systems, and obviously plastic littering of plastic is part of that. So there are some regulation, but it's not specific to microplastic. However, there's a lot. I mean, every day you see new papers and new evidence showing, you know, the possible impacts of plastic in human health or ecological risk. So all that information is taken into consideration, and EPA is actively, you know, taking that information and trying to figure it out if the, you know, microplastics are going to go into some of this more specific regulation standards. Okay, so I think that maybe also you have seen this microplastic. We have two types. There are the primary sources. Well, first, you know, it's a little bit random. We call microplastic everything that is a small of 5 millimeters. Who came with that definition? We are not really sure, but somebody say 5 millimeters, and we all say, okay, yes. So everything below 5 millimeters is going to be a microplastic. And not all microplastic start a microplastic. You know, there are primary sources that mean that microplastic that they have always been microplastic, and then they are released into the environment. And there are secondary sources, meaning that you have a larger piece of plastic and it breaks down into little microplastic, you know, smaller particles. And also we have different geometrical configuration. There are fiber, pellet, films, fragment, foam, microbeads, etc. So it has a very large and broad family of particles that we are talking about. So some primary sources, you know, cosmetic, fibers from clothing, and industrial are the main sources of primary microplastics. So microplastics, and you know, at the manufacturing level, they are very useful for very different applications. So they are used pretty extensively in different materials or operations. So how the secondary microplastic are produced? There are photodegradation. Plastics are made to be stable. They don't interact really with too many things. Actually, we use it as a microwave container, because they don't have any heat transfer. They don't really absorb any type of energy. So they are very difficult to break. And the only effective agent that it break down the polymers are going to be UV lights. The sun is the best. Photodegradation is the more effective method to break down the chemical bonds that you can find in the polymers. But also there are going to be physical degradation as the plastic. If you later plastic, it's going to be moving through the different surfaces and through abrasion and collisions, and it's going to be forming different type of smaller particles. Also the freezing and freezing and defreezing, thawing process also help to create fractures, because material contract and then expand. That start creating a little bit fractures and increase the chances of breakage. And also when you have this micro, fractures in the plastic, it's easier for you're increasing the surface area. So they give you more chances to organisms to start growing, to forming biofilm, and actually selecting organisms that they are going to have some chances to use some of this polymer as a carbon source or energy source. So all of these three are, commonly common processes to produce the microplastics, but I would say the photodegradation and physical degradation are the most, the ones that they contribute the most for it. Something that I wanted to show you to put it in context, again, microplastics are made to last. So most of them, the natural degradation rate, they tend to be in a very large, in the orders of hundreds years to complete the degradation. Now, this is interesting to think about because as I showed you in the first graph, we had been producing, manufacturing and industrial level plastics since the 1950s. So it's about 70 years, that they had been around. So we haven't really reached the degradation that even, the halfway and sometimes of this materials. Now, something that we need to consider, the plastic that they are releasing in the environment are not only the polymer that it is, and that we study, they are not polystyrene, there are going to be other materials. For example, there are going to be a series of dyes or pigment. Some of the dyes are going to be organic. Some of them, they are heavy, they are metal based. They are stabilizers. They are plasticizers. So all of these materials most likely they have not been released from the matrix of this plastic. So we are not at the time frame, that we need another 100 years to start seeing how much of this are going to be released into the environment. So that is something to consider. When we think about plastic, we only think about the polymers, but also remember that there's a lot of things in this plastic that most likely they have not been released yet. So we haven't seen the full range of impacts, I think, that this microplastic can have in the future. Okay, so now let's come back to what we do is the wastewater systems. So primary sources and secondary sources of microplastic can enter through different routes to wastewater treatment plants. So in the central part, you see what it looks at wastewater treatment plants. So we have different systems that they are going to be promoting the action of biological material. And then we basically try to settle everything on it. And then we discharge the water and it can enter to freshwater systems. So that's again another ways to show this, and also it can be entered into the ocean as well. So this is a little bit more schematic. What you see if you have never been in a wastewater treatment plant. A wastewater treatment plant is not a single step. There are multiple steps. All the steps are based, especially the first two, are based into the physical separation. We start in the primary treatment, we basically have screens or large filters that it take like the big things that they enter to wastewater treatment plant. If you have never been in a wastewater treatment plant, I recommend you to visit because it's so interesting to see what people put in the sewage. I mean, you will never imagine what things that appear in that first stage of in the preliminary treatment system. And it's crazy. I mean, everything that you can imagine. Then we separate the liquid from the solid, and then we go to another stage in which we promote the growth of microorganisms, and they eat the material that is going to be dissolved, but in a small pieces. So think about if you have water with sugar, how you get rid of the sugar. So what we are doing in this wastewater treatment plant, anything that is going to be dissolved is going to be transformed into bacteria, into a solid mass that then we can separate using a sedimentation tank. So we are just changing the phase mostly of the contaminants from the dissolved and in very small particles to bacteria, and usually bacteria get together and they form flux. So that flux then it can be easily removed from the wastewater treatment plant. Then when we separate it, the liquid then go to disinfection because there's still a large amount of bacteria in there because they are very tiny too, so they can pass. And the solid part is going to be to a solid waste management. And some of that, a large amount of solid waste from the wastewater treatment plant is going to be maybe used for agricultural purposes. If there are not too many contaminants. If there are a lot of contaminants, they need to go to incineration or landfilling. So here we have two emissions to the environment, a liquid stream and then a solid stream. So the liquid stream, again, there's still going to be a lot of small particles, and it's estimated that about several millions of microplastics are releasing every day for any single wastewater treatment plant. Now, maybe more importantly, when we dispose that sludge into agricultural systems, every time that it rains, there's going to be agricultural runoff, and some of this microplastic that they were a little bit bigger and they were trapped in the solid during the sedimentation stage, they are going to be released again to the environment. So again, we have two routes for entering. So we are not really treating the microplastic in our wastewater treatment plant. That we are separating into very small and not so small particle. Okay, so this is some results about a study that we did about 2 years ago, in which we tried to see what is the stage. I mean, do we know how much microplastics are released from wastewater treatment plant? And we tried to collect all the studies that they were at the time. And we got about 93 studies that they were covering 93 wastewater treatment plants, most of them from the northern hemispheres and developed country, and so not too much still in like a lower economic developed countries. So this is the at that time that what it was available, and we have the southern hemisphere, we have some wastewater treatment plant in Australia, but Australia is a much more developed country compared to all the rest of the other countries in the southern hemisphere. So some results that we found a lot of discrepancy in terms of how the samples from this wastewater treatment plants were collected. So in other words, there were not a comprehensive or a guideline about where and how you're going to be taking the samples from this wastewater treatment plant. And that could be a problem because, as I show you in the train of treatment, it will depend a lot where you're taking the sample is going to give you the concentration of the wastewater treatment plant. Sometimes why they are not taking it in the discharge of the section of the wastewater treatment plant. It might be just practical. It's very, as you can imagine, it's not that easy to have access to the pipe that is discharging the wastewater treatment plant. So it might be something that is not as easy. But in general, we did not see a consensus in terms of how you need to be, how long, how much. None of them is really standardized, or there were not a guideline at the time, at least for wastewater treatment system again. Another thing that we After you take the sample, you need to treat. We need to try to separate the microplastic for everything else that is in the wastewater. As you can imagine, there's still a lot of things there. We also saw some discrepancies based on how they were separated or treated, even though the NOAA method, that is this, maybe if you are working on microplastics, you know about this method. It was the most commonly used. There were still, several researchers out or several studies that they were used just simple filtration without the removal or without doing all this extensive pre-treatment that it usually is required for the to identify, to isolate the microplastics. Other important thing that we noticed as there were several studies that they did not have appropriate quality control or quality assurance system. As you can imagine, microplastics are everywhere. So not to freak you out, but you are breathing microplastic right now, either from the clothing that you have, shedding of the materials of the paint that is happening in your room. So, I mean, if you take a sample and you open it in this room, you are going to have contamination from the room. So we need to have extensive, and I think maybe Professor Suckling talked about it, then we need really intensive, quality control and quality assurance system. Several studies did not have that. So, we start having some conflict about what is the quality of the information that we were getting. Also, how they were identifying the microplastic. As you can see, about 50% of the studies, they did just visual inspection. They use a microscope, and they say, they were they were not using tools to actually identify the polymer that the particle have. So they were just saying this looked like a microplastic, and they checked the box, but they were not really identifying the polymer source of this plastic. And the other three, FTIR, Raman, spectroscopy are the most common method used to identify the polymer nature of the particles. And they were also not even half of the studies were using that method. In terms of sizes, also we found some differences in most of this. I'm sorry, this is the amount. We found some differences. We think that some studies found between 0.1 to 0.5 per liter. I mean, we should have put in per gallon, but multiply by 4, and you would have gallons here. So we didn't found that many. In general, they were not reported not that many microplastics. But if you look on the sizes that they were reported, there were most of the study more than more than 90% of the study, they were only reporting the large fraction of microplastics. So this is not, if you go below the 25 micrometers, you are getting much more, a larger number of particles. Also, what you see here in the pie chart is the composition of the different polymers. So you find pretty much any type of polymer that you can imagine from plastics. However, since they are wastewater treatment plant and these were urban wastewater treatment plant, the dominant geometry for these particles were fibers that they were, originating from clothing. So this is something that they have in common, all the studies, that in general, we know that the large fraction of microplastic that there are in wastewater treatment plant are going to be coming from the washing of synthetic clothing. The other fractions are going to be flakes, and this can come from from different sources. Washing dishes that they are plastic. Any type of surface or film that cover any type of material that is plastic, and we watch it. It's going to be starting showing there. Okay, so this is also beside during the study with the wastewater treatment plant. There were not that many studies at the time for drinking water, and we find a very few number of studies that we couldn't do the same type of graph that we did with the wastewater treatment plant. But interestingly, what we found is the report of microplastic, for example, in bottled water, are much higher. They found much more microplastic in bottled water that you will find in a wastewater treatment plant? Well, it makes sense because, bottled water is usually, in a plastic bottle. So there are going to be particles that are going to be transferred either through the processing. This water is extensively processed. So yes, you're going to find, microplastic there, for different sources. Tap water also show a very large number of particles. I mean, there were systems that they did not show any, but this is only a couple of studies. Other studies show like 61 microparticles per liter. Also, if you think, it will depend where are you taking the sample of the water. Most likely samples that they are taken at the tap, at the point of consumption, they will have larger amount of microplastic because the pipings in houses indoor, are all PVC. So also it makes sense. So I think there will be a factor of aging. The older the PVC pipes are placed, I will make pretty much sure that there are going to be a larger amount of plastic. Or also maybe new pipes also can be releasing a lot of them, and then after a while, I don't know if you know, but your drinking water pipes are covered in microplastic or some salts around. They are not perfectly clean. That it might help to stop the process. But in general, aging is going to be an issue in both sides. Too new, too old. They both can be contributing large amount of microplastic. Again, in this studies, because they knew that they were going to be quantifying a smaller amount, we think that most of the studies have better quality control and quality assurance. So these numbers are good. However, the number of studies were not enough to do any type of major assessment. So let's come back a little bit to this wastewater treatment plan. And I already mentioned that what we are doing is basically separating the microplastics because we're not treating them. We cannot remove it. We cannot really degrade it too much in a wastewater treatment plant. So we separate it for the small ones that they cannot settle in this last stage of treatment, and the ones that they were large enough that they get trapped with the bacteria, and we separate in the solid phase. But then both of them, they are going to be entering to the environment by different routes. So we can say pretty clear that wastewater and stormwater also, infrastructure is not really designed to remove microplastic. And why? It's mostly the main, there are different mechanisms, but we rely heavily on sedimentation, and that the particles are large enough so they are going to be settling and we will be able to remove it and separate it. Now, if we're thinking about microplastics, they are very small. And also the density of the microplastic is very similar than the density of water. The proof is like when you have some plastic, they usually float. There are not that many plastic that they are much heavier than water. So they tend to float. So as you can imagine, very small, not too much difference of density. Gravity doesn't make too much of at the time scale and size scale. This microplastic don't even see the settling tank. So we need to find some other way, we need to try to figure out how we can remove this fraction of microplastic that not relied on gravity or in density differences. So what we study is the use of this process called electrocoagulation. And electrocoagulation, it consists, and we have two electrodes, an anode and a cathode, and then we apply a voltage difference between two of them. So there's going to be some current going into stuff. We're going to have some electrons be taken from the cathode. They're going to be transferred to the anode, and there are going to be some release of electrons from the anode. During this process, when this happens in the cathode, there's going to be the production of some micro bubbles. Most of them, they happen because of the dissociation of the oxygen molecules, and you are going to be producing micro bubbles of hydrogen. On the other side, if we have, for example, aluminum anode, it's going to be releasing aluminum ions. Now, it happened to be useful because aluminum is a very good flocculant, meaning that it forms some type of network when it's in water. So now we have this network, like a filament that it gets formed with the, if we want to call it like that, like a little bit of flux that is happening, and with because of the speciation of the aluminum. And then we have this bubble. So what happened is that we can trap things with this mesh of aluminum, and then the micro bubbles are going to be lifting this up. So that's what we were hoping that we wanted to study. Will this be effective to remove microplastic from wastewater system? So the idea will be that could we add this to as a next step after the sedimentation, the last step, to remove this microplastic from, so it will be an upgrade for the treatment of wastewater treatment plant. So this is what we did. Obviously, you start with a very small systems, and yes, this is a mason jar that we identified. So obviously we couldn't use anything plastic, so we have to use a glass jar and some Teflon that we know that we are not going to be adding to the system, and that's what we're expecting to do. We use microplastic of different size. Actually, this is another study that I don't think I will have time to show, but actually we use glitter that different glitter size have different colors. So we were able to identify, the different colors based on the different sizes based on the color. So again, we have our mixture of plastic, of microplastics and water. We applied our different voltage and we, produced that. But how much we are going to be removing was the question. And this, you have a picture of the before and after. And this, so this is how it looks a little bit. And this is our glitter, which interestingly enough, we learned that also in this type of, this is a very small glitter, and is the color that you see is given by titanium dioxide. It was full of nanoparticles. So it's extremely stable. It was very difficult to degrade. So just summarize it, I'm showing some of the main results that we obtained. This was with wastewater collected from a wastewater treatment plant here in Rhode Island. We have, so this peak that you see over time is when, all the flocculation gets formed. So we have an increase of the turbidity, but then as the bubbles start forming, we see a reduction of the, we see how the water is getting clearer and clearer in our system. And we were able to remove about close to 97% of whatever it was left, the particles that they were left from the wastewater treatment plant. Now, something interesting that we can see here in the table, we see, we remove, well, in this case was 94 for the after chlorination. Interestingly enough, we were able also to improve the quality of other parameters that they could be possible contaminants in wastewater. For example, the COD is what is called the chemical oxygen demand, and it's an indirect way to measure organic matter that is still left in the water. Using this method, the electrocoagulation, we were also able to remove even further the amount of organic matter on it. And also we reduce still, there's a lot of bacteria per liter still in the effluent of our wastewater treatment plant. And again, we were able to improve the quality of this water. So we thought that this could be an interesting alternative because not only bring benefits in the separation of this microplastic, but also we are improving the quality of this effluent and maybe it could be reused, that now I give you an idea of a much more closer to a fresh water system, if we want to call it that, it was before the treatment. So again, we are relying now in flotation instead of sedimentation. And plus, again, we don't target a single just microplastic. You can remove other contaminants too. Okay, so just to finish here, if you are more interested about all this information, there are much more. Much more. I could talk forever about these two studies. But we recently published this two. This two study, the overall, the review of what's going on with wastewater and drinking water in terms of microplastic amount and analysis, and also this new technology that's not new, it's pretty old, but the application of this electrocoagulation for wastewater treatment plant. And with that, I will be glad to answer any question. And also, so before I go, I need to give credit to Dunia El Khatib, which is the graduate student who did all the work here on this. Really, I'm just delivering, try to deliver what she, presented what she, her really great results. And thank you. And again, now for sure, any questions that you can have.
Thanks, Vinka. Can everybody turn your cameras on for a round of applause, please, to acknowledge her?
You can do that like this.
Hey, hey. And I'll open the floor to questions before I jump into mine. So anybody from the audience have questions for Dr. Craver?
I have one that I think is probably pretty self-evident. Hi, Vinka.
Hey.
What's the impediment to having wastewater treatments start employing this? Is it financial or retooling? Would things have to be retooled at the plant, or what's the impediment situation look like?
I think all of the above. There's going to be financial, and again, I think the biggest limitation is there's no regulation. Wastewater treatment plant right now, they are not required to treat for microplastic. Microplastic from the law perspective or regulation, they are not contaminants so far. So that's one. If they get implemented, then certainly it's going to be an incentive. However, and that's why we are trying to look technologies that they are not, you need to convince them. They have to be economically effective for them to use it. And also wastewater, water and wastewater sector and facilities, because they are so heavily regulated, they tend to be very reluctant of new technology. So you need to completely prove, that this stuff is going to work, but they are not going to jump into new technology. So even though you can have a really good technology can work, it's going to take, I think, several years, and you go first to pilot plants and stuff. So it's not very fast moving sector, I would say.
Thank you. Great talk. Thank you so much.
Thank you.
Hey, Vinka, what happens with the flocculant after it's done? All the microplastics are now in this top layer. It has to be disposed of. I mean, we sort of seem stuck in this sort of just in the end, if it doesn't break down, we're just moving it around the different places, right?
Yeah. So obviously this type of, measures, it cannot be implemented without source reduction. I think that's not, like you say, we keep going and the stuff. It's very, from the wastewater point of view, the only tool that we have is separated. And we look for different methods to separate it. Yes, you are right. There are going to be challenges of when to release, where we're going to dispose this aluminum. We might be, they can be used for, I think that there are different applications that they could be used for the aluminum. There are other type of materials here, so you can do iron-based anodes. So they are, they are a little bit less, aluminum have a connotation because, there are this linkage with Alzheimer and other things. So people don't like so much aluminum now. But yeah, you're right. We need to figure out what to do with the solid waste. Most likely it's going to go, we need to reduce sizes, and where we're going to place it, most likely either will go to a landfill or an incinerator. That's what we have. So again, I mean, what I see it, is wastewater is the last resort. I mean, we try to separate as much as we can before we release it to the environment. But I think that we need to work a lot in the source resort. I mean, you cannot rely on solving the problem of microplastic at the wastewater treatment level. I mean, you are too late.
Yeah.
For that. But it's what it's what we can do. It's not going to be perfect. The only thing that we can do is kind of separate and move things around, and if you don't separate and you start adding energy, so you start creating other sort of problems if you want to destroy the microplastic. So it's not a benign. I mean, every single thing that we will try is going to have an impact. Basically, you're moving things around. The impacts you are moving it around, and then you need to find what is the solution that it brings the less secondary impact for global and for your local community too.
Just stop using plastic is what you're saying.
Well, you need to use plastic for certain things, you know. I mean, if I go to the hospital, I will appreciate to single-use plastic. I don't want to reuse anything from them. But you know, like straws or single-use forks and stuff. Yeah, I mean, I think we can make it. Yeah.
Are there? I imagine there's work being done on it, but are there microbes that will effectively completely break down the polymers?
There are some studies, so they had found some activity to for a specific type of polymer, because every polymer have different, chemical bonds and chemical configurations. So there's not going to be a single microorganism that it will be able to break all the polymers. So they tend to be, so far, for what I have read, they tend to be very specific. The PET microbes on the polystyrene microbes, so that but we don't have one that they will be able to remove. I mean, they are, and I think, if you don't know me, I think that bacteria can do everything, if you give them enough time. And so, yeah, I think that whatever you find, you will find activity. Now, again, it's not easy. I mean, because of the time frame that a bacteria live, compared to the stability, the chemical bond stability of the microplastic, the plastic in general, it's much more different. The poor bacteria can do something, but it's not that easy for them to work. So I think that usually what we try to do, and this is for anything in environmental engineer, we do like this sequence, this change of treatments, that you use one mechanism, then another mechanism, then you keep changing things to try to attack the problem or the contaminant from different places, so you have more chances to break it. So I think a strategy to a single step, it might not be the more effective. Usually you want to use a multi-step system.
Great, thank you. Other questions? All right, I guess that's going to do it. Well, thanks again, Dr. Craver. And thanks everybody for attending. And so this has been recorded. I started a little late. You probably saw the notification, but we will post it for those of you who want to rewatch it, or to those of you who know people who weren't here, they'll be able to see it there. And really appreciate your time and your expertise, Dr. Craver, for joining us today. Any final comments or questions?
Yeah, don't use too much plastic.
Right. Yeah,
think about all of the, what you hear, think about where that plastic, where it goes, and then eventually you're drinking that. Right. Whatever you use, it will come back to you. It's like karma. It will come back. Whatever it will come back to you. Yeah.
Right. Yeah, right. Reduce that's the most important part of the whole thing, right? Reduce it all. So, all right. All right, everybody. Thank you, and hope to see you next week at next week's brown bag.
Okay.
Bye, everybody.
Bye.